Assalamu alaikum. Once again, welcome back to my channel, BrainGain. This time we are going to discuss about Yagi-Uda antenna, that is the linear dipole array. I have made it here. This structure we are going to make and how dipole is made. Actually, we are going to see through it. I have a thing. This is Yagi-Uda antenna. There can be number of reflectors and number of directors, but only the feeder is one dipole, as we have made dipole certain in the last video I made dipole with coaxial balance. The dipole will be of the same thing, and the, this is the they all will be of the same material. And we have this time we have number of directors three, and one feeder and one reflector. So I have some sort of uh, equations for it. Yeah, we have frequency, we have lambda. I have frequency of 2 gigahertz, lambda is 150 mm. Total number of elements is 5. Number of directors we have 3. Number of reflectors is 1. The number of exciters, that is excitation, is also a direct feeder, that is reflector is 1, and the feeder is actually the exciter. So total length of reflector would be 0.5 lambda, and total length of feeder should be 0.47 lambda, and total length of each director should be 0.406 lambda, and total spacing between reflector and feeder should be 0.25 lambda, and spacing and this all these things. So we are going to go to CST, go to this section should be open with you, new template, and microwave antenna. We're going to dipole. Dipole is actually a wire. We're going to use wire antenna. We are going within time domain. Next, these are the units. That is normal routine. And the next, and as my frequency is 2 gigahertz center, so I will take the frequency range of 1 gigahertz to 3 gigahertz. Next, and finish it out. You should be seeing out that uh, let me talk about one more thing. What is spacing between reflectors and feeder? 0.25 lambda. So 0.25 lambda. I have in this simulation, I have that is as 0.5 lambda distance between reflector and feeder. So I am going to make it at 0.25 lambda. So 0.25 lambda. Okay. You post processing. Okay, simulation. The results. Yes, yes, you have to wait. I'm just going to make another file. Simulation start and let it run in background. Okay, the first thing we have to make a feeder. Feeder mean the actual dipole. So what would be the length of the feeder? It should be 0.47 lambda. And you see the length of reflector is greater than the feeder, and the length of the directors is less than that of feeder. So in length, reflectors have more length than feeder or director, and the feeder has a length smaller than that of feeder and reflector. Director. Director has small length and reflectors have large length. So we are going to make enter the parameters. I have lambda of 150 mm. So I will enter my parameters. That is, number one is total length of reflector. So length of reflector is 0.5 lambda. Length of reflector LR is the length of reflector, that is 0.5 steric lambda. Okay, we are going to add next parameter, that is total length of feeder LF 0.47 lambda, LF 0.47 steric lambda. So what is our next parameter? Length of director 0.406 lambda. Length of director 0.406 steric lambda. So next thing is the distance between or spacing between the reflector and feeder, how much the gap should be there. That I am going to represent it by SRF. That is spacing between reflector and feeder. That is 0.25 lambda. You can see it. And spacing between adjacent directors. That will also be the spacing between director and feeder and between two directors. That is SDD I will represent it. 0.34 lambda. SDD 0.34 lambda. Then we have radius A, that is radius of the dipole, and it is 0.003 steric lambda. I have to confirm it also. Yes, 0.003 lambda. Okay. So what about the gap between the dipole? You have seen in that I have made the dipole with the coaxial balun in the last video. In that I have used the gap is equal to length of the dipole divided by 200. So in this system, we have the length of dipole as uh, length of feeder actually. That should be LF. Uh, so this is going to be gap, that is capital G, and that should be LF by over 200. Okay. So now we are going to see that. Now I'm going to go to modeling mixed cylinder. That is, name it as dipole. It should be 0 to radius A, extended is 0 0. Z minimum is G by 2, cap by 2, 2. So length of feeder divided by 2, and it should be PEC. Okay, you can see that I have made this table. Next I am going to select this, go to components, component 1, select your dipole, go to transform and have mirror it, copy in direction of Z, have a preview. You can see that we are having another dipole in this region, and there will also PEC and other things. Okay, so we have made two arms dipole with a gap of G by 2 in between. Then G by 2 is there and G by 2 is the total gap. I can again show you the parameters. That is 0 to A is the radius of the arm, and by xy center that is in the center of the plane, and G by 2 length of feeder divided by 2, and other length of feeder divided by 2 will be there, so it will be actually length total. So for confirming it, I will go there, components, that of feeder, that is actually the dipole, we have made it there. like that. So we have made it. Now we need to make the reflector. Again we will go to cylinder, that is reflector. It should also be of radius a. It should be in center with respect to x, but it should have some distance in y plane uh, with respect to our uh, main dipole, and that space is SRF, spacing between reflector and feeder. And it will start from minus length of reflector divided by 2 to length of reflector divided by 2. It should also be BC, and you can see that is okay. This is, I can show you up. This is the reflector we have made. Okay. So now we are going to make the director. Go to again to cylinder. Press escape for it. This is director 1. This is again A, and we are going to spacing between the feeder and the director should be STD. Okay, one more thing. I The reflector will be on one side and the directors should be on one side. So I am taking directors in positive side and the reflector that's on the back side. So we have to put with SRF the spacing between reflector and feeder as negative. So it should set minimum should be minus length of director by 2, and here should be length of director by 2. It should be like preview. Okay. So go to reflector and define cylinder, edit. It should be minus SRF in preview. So now you can see that reflector is on the other side and director is on the other side. Press OK and close. So this is now reflector, and this is feeder, and this is the number 1 director. Now I'm going to, we need 2 more directors. So this is director 2. It should radius A. It have a distance of 2 STD, and it should also start from length of minus length of director divided by 2 to plus length of director divided by 2. We say OK. Now you can see we have this reflector, this feeder, and these are 2 directors. We need another director. We go to, so this will be director 3. Again the radius of A, and this will be 3 steric STD, and this will be minus LD by 2 to LD by 2. So it should be uniform from minus S to plus S. Okay. Now you can see that we have another director. This is the director 1, director 2, director 3. This is dipole, and this is that is feeder, and this is the reflector. Now we need to give uh, excitation to our dipole. For that, I little need to move out my dipole. Again, zoom them. So you can go to pick and pick what pick. Go to this pick points. Pick face center. That is this center. I need to move it little and just need to move it out. Uh, I need to move it little go to again pick points and pick face center, now this and this center, and go to the simulation and this create chord between these 2 points, 50 ohm match. So this is the here, and now we have made it on. Then you can apply your post go to modeling, yes, simulation. You can apply field monitors, far field, and your own frequency 2 gigahertz, my frequency. So press OK, and after that you can go to setup simulation. And you can start your simulation. So, but I have simulated it here, and I have the results. You can see that the results will vary little. This is away from 2 gigahertz. That is my center frequency. So that is not the point to vary. Okay. Then we will go out for far field results. You can see that absolute. We're gonna see it out. Yes. This is, we can see the Yagi-Uda antenna array gives uh, 10.6 dBi gain at our frequency of 2 gigahertz, and it is more directive than simple dipole. Simple dipole have the donut shapes radiation pattern. So, okay, we what to do to tune it? Go to the S1 parameter. We see that at our 2 gigahertz frequency, if we use the marker M and double click, we got the marker. At 2 gigahertz, we have minus 9.7 ASX. It is almost matched, but if we want to shift this dip to our desired frequency, what we need to do is go to your 3D model and uh, go to components. Okay, so you can go to optimizer, not optimizer, go to parametric sweep and go to new sequence, the new parameter. I've already made this parameter, and then add it. Go to for SRF, that is the distance between the reflector and feeder. Okay, so linear sweep. Okay, for to enable it, this should not be, SRF should not be in terms of lambda. Okay, if it will be in terms of lambda, you cannot have the parametric sweep parameter. So make it sure that it should be written in this form of 0.25 multiplied by lambda means 150. You can specify the value to start from 18.75 to end on the 112.5. I have done so, and in how much steps it should go there. Then go to start, press OK, and then start the parametric sweep. It will be going to give you the results of parametric sweep. So I go out there and I have that parametric sweep, and you can see this. These are my results. Okay. So from this I can see that at this way parametric sweep of SRF, the distance between reflector and feeder of 100 mm. Distance is 100 mm. I'm getting that dip near 2 uh, gigahertz, and if I make it this S11, this S11 is also near 2 gigahertz, and this is at 65.625 uh, gigahertz. So I want to have uh, I want the value, but I need the value close to 65.625. That is 75 mm should be the right value. That is actually 0.5 lambda. Okay, that's 7. Update your structure. Delete your previous results by going to post processing, simulation, and setup solver and start your. You have to wait for it. In video, you can skip this part and just go on to see the results. I am just adding I'm my video is taking this time. So if you need some tutorials more related to another antenna design simulation solver, that is HFSS, using being used in market, you can um, demand it in the comments, and surely we will do our best to help you out in antenna related problems. We can design on reflectors, we can design on frequency grain fee, we can define patch antennas, horn antennas, conical and pyramidal horn, and other antennas as well, whatever is in the market. So at 75 you will notice that the results are so much accurate. Let me see how much this has taken 21 minutes, not a big deal. Always use your parameters like this, uh, so you can just edit your parameters from here. Every time you don't need to double click it and then go to like this, double click it and go to define cylinder and edit it, and you can define new uh, access system in it also to work with a reference that I used to prefer with to work with on global reference. I know where to place things with a global access, that is 000, the actual zeros. So our antenna is just going to be simulated. And after editing these parameters, you have to press F7 to update your structure. You should learn from Alanis book and Mozart book. These are interesting. See how much your structure is large. The simulation will take more time according to that. Just our simulation is just to complete. Then you can go your parameters and see your S parameter that I have got my tape near my center frequency that is of 2 gigahertz, and it is the dip is about minus 16 dB, and at that time we are just happy. we were having minus 9 dB and now minus 16 dB. So we have tuned it out at our center frequency, and now we go to far field sleeve. You can see this time our gain has been compromised, that is 6.29 dB. And whatever I want to show you the structure and make far field structure. You can see this. You can see this is the dipole, and these are the directors, and here is the reflector, and you are having this type of structure directive in the direction of directors. So we will end up our video here. Thank you for watching. Hope for the best. Allah Hafiz.